Okay, can everyone see my screen?
Yes,
Yep.
I can see your screen.
I can see it.
Okay, cool. So let's get started. Today we're gonna do some combination problems. But first we're gonna go over some of the quiz questions from quiz 3. The first one is gonna be problem 1. I'm sure you have all read the question. So basically we just want to prove that P0 dot A sub n is equal to P0 for all n is greater or equal to 1. And we have the induction steps. We have the induction statement here. And we're going to first start with the base case, show that P1 is true. So let's write out what P1 is. We substitute this. We have P0 dot A1. And we know that A1, we're going to use the definition of AK here. That P0 times P1 plus A0. Okay. And then let's see, like we assume that A0 is equal to P0. So we can substitute that in, which we got P0 times P1 plus P0. Okay. And then we can use the rule in the table, which is the first one, commutative. You can switch the order of these two. And then I'm just going to write here. I'm going to use absorption, and which is just give us P0. This is J. Okay. Here's the absorption. This one. All right. Base case should be pretty straightforward. And then we have the induction hypothesis is assume that Pn minus 1 is true. And we want to show that Pn is true, assuming Pn minus 1 is true. So we first start with our Pn. We write out what Pn is. So Pn is P0 dot An. And we substitute An is equal to Pn plus An minus 1 again. Just from the definition of AK. Okay. And since we assume that Pn minus 1 is true, I can just write out what Pn minus 1 is here. So Pn minus 1 is okay. So which this is equal to Pn plus P0. Which is by the induction of hypothesis. Okay. And then you can just do the same as you prove for P1. You just switch the order. and use A here. And you would get P0 for absorption. And you're done. Any question?
Yeah, how'd you get that A of n minus 1 is equal to P0?
So we have assumed that the Pn minus 1 is true. So if we, let's see. If we substitute the A sub n minus 1 into this formula, that would be P0 dot A1 minus 1 equals P0. And oh, I see. So I think interesting. So I see. If we do Pn, if right here we write out the, oops. Stop. If we write out the P0 dot Pn plus P0 dot A sub n minus 1, and it will give us P0n, Pn, and plus P0. It is correct. And from this step, let's see. If we okay. If we take out the P0, and that will give us, in this part, you will use Pn plus 1, which is universal bound, and that's I. And this will give you, well, not this, the next step will use universal bound, which give you, which give you 1. Okay, and then next step, you're gonna use identity to get P0. And that's D. Okay, just ignore this part. I think the solution is wrong. Okay. This should be correct. Is it Faye?
Yes, I'm pretty sure the second one is correct. I'm not sure about the first one.
Yeah, okay. Just ignore this part. Any other question?
That was a really good question. Somebody caught that. That's really good.
Thank you. I didn't even realize that when I was go over this question with the old solution.
Yeah.
Okay. Next one is problem 6. So we're given the 3 sets ABC, and want to use the anonymized proof to show that A union B equals C. And we want to first show that A union B is a subset of C. So the first one, I want to show this. And if we start with let XY belongs to A union B, where you have XY is integer. Okay. And since your XY is in A union B, which means that your XY must be in A and also in B. So you can have X minus Y is equal to 2K, since XY is in A. And you also have X minus Y equals to 3L. And since your X and Y is in B. And then, okay, now you can see that 2K equals to 3L. So what do you notice about L here?
It is divisible by 3.
Your L? We're not sure if L is divisible by 3 or not. Your 2K is divisible by 3 though. But what do you notice about L itself? Based on 3 times L is equal to 2K. What is special about 2K?
L must be an even number.
Yes, exactly. Because your 3 here is an odd number. So your L must be an even number to make it the 3L to be even. So you can see, okay, L must be some even number. You can say that L is equal to 2M, where M is an integer. And then you can substitute this back to this one, to X minus Y. So you have X minus Y equal to 3 times 2M. And that's equal to 6M. And then you can conclude that your XY is in C. So XY in C. Okay. And you're done with the first part of the proof. And the second one, I want to show that C is a subset of A union B. So let X and Y in C such that XY is all integer. And we have, based on the definition of C, we have X minus Y is equal to 6N, where your N is integer. And then you can rewrite this as 3 times 2N. Okay, and here you will have 3, or just by closure, 3R. So this shows that your XY must be in B. Okay, and then Well, we can also rewrite this as 2 times 3n. And you can also conclude that by closure, you have 2r, which is x and y, is also in A. So since x and y are in both A and B, which means that your x and y must be in the union of A and B. Yeah, sorry, in the intersection. And then you can say, okay, now I have A intersects B is equal to C. And you're done. Okay, any question about this one? All right, so so before we start doing the probability and combinations, I actually want to write out a table, and I hope everyone can write this down because it's an important table. I'm sure you have like seen some part of this table in the lecture slides, but it's just nice. We can just go over together here. Okay. So suppose that we want to choose R item out of n possibilities. Okay, and here's your 2 variables, R and N. So we have 4 different types of rules that we can use. Do this and okay. So I'm gonna write on this handstand like repetition as R, and the next column I'm gonna without repetition, which means repetition are not allowed. And this part is gonna be order, and this is on order. Okay, so how do we name if something is ordered and repetition also allowed? What do we call it? It's just an order list. And then what about something is unordered and you can have repetition? It's a type of problem which is pretty common. So we can usually call it a bag problem. Or to find out like how many possible solutions to an equation. So, and the next one is without repetition, but the order matters here. What do we call this one?
Permutation.
Yep, permutation. And what about the last one? Anyone see in the chat? You can use a combination or you can call it a set problem. which the order doesn't matter, and you cannot have repeats. Okay. And right now, here comes the key part. How do we write out the general formula of this for? So if you have like an order list and you want to choose R items out of n possibilities, does anyone know how would you write out the formula for this one?
That would just be n to the power of r, right?
Yes. N to the R power. And what about the bags problem? The order doesn't matter, and you can't have repeats. So we're gonna use this formula. R plus n minus 1, choose R. And I hope you know how to compute this one. Oops. Okay. And what about the formula for permutation?
Would that just be P of nr?
If you write that out, that's n factorial over n minus r factorial. And what about the set? Anyone know?
Combination of, so C, N, and R.
Yep. Okay. And now let's go back to the problem. So for this one, it says, how many binary sequences of a length at most 5 have exactly 3 ones?
Can you scroll back down just for one moment, please?
Yeah. You can take a screenshot or take a picture if you don't have time. Is that okay? I scroll back. Okay. So how many binary sequence of a length at most 5 have exactly 3 ones? And right here, you notice that we have the at most 5. What does this imply about our length of binary sequence? And we also have to have exactly 3 ones. What does this imply about our length of binary sequence?
The length can be between 3 and 5.
Yep. So the length of the binary sequence can be 3, 4, or 5. So for length of 3, what are we going to use for just think about the table. Which one are we going to use to find out how many ones are there? How many ways of binary sequence you can form? Which one you're going to use? Is it permutation? Is it set or order list or bag problem?
Would it be an ordered list?
So a binary sequence, let's see if we have 3 spots here. And we can put either 1 or 0. So the order matters basically means that your 1, 1, 0 is different than 1, 1, 0. But in binary, they're the same. So the order doesn't matter here. And you can have repeats. Well, you cannot have repetition. So we'll come down to a set problem, which you want to do that your C is 3, choose 3, because you want to have exactly 3 ones. The reason why you cannot have repeats is because that if you already choose the first one as 1, you cannot choose the second time. Okay, and that will give us the how many possible ways to form the binary sequence with the length 3. And yeah, go ahead.
No, it's okay. You can go ahead and do it.
Okay. So if you have length 4, similar, it's gonna be 4, choose 3, since we have 4 spots right now. And we want to choose 3 of them to be 1. And similar for length 5, that will be 5, choose 3. Okay, and then you will use the rule of sum to add these 3 together. So 3, 3 plus C4, choose 3, plus C5, choose 3, which will eventually give you 15. Any question about the first one? About part A?
Can you explain why the order doesn't matter? Because wouldn't 110 and 101 be different binary sequences, so order would matter?
Yeah, so the order matters is when, it only matters when you, it would be the same if you first choose 1 as the first spot and then choose 1 as second spot, but it's the same. So, okay, so if I want to pick 3 ones from these 3 spots, so the first spot I pick is number 2. So I pick this one as 1. That is my first pick. And then I want to pick a second spot, which I pick this one. It's the same as you first pick this one and second pick this one. You will all have 0, 1, 1, 0, 1, 1. The outcome is the same. That's why the order doesn't matter. The order basically means the order you're gonna choose, the order you choose which one first.
Okay, that makes sense. Thank you.
Mm-hmm.
Could you also explain why it's without repetition, given that it's only comprised of 0s and 1s?
Yeah, so we have 3 spots here. And if we first choose the second spot as our 1, so that basically means you already picked this one and you cannot pick it again. Repetition basically means you can pick a second time of the same thing. In this case, would be in the same spot.
But aren't all 1s the same?
Well, we're picking from these 3 spots, not from ones. So it's out of 2 possibilities, and we want to choose 3. So Okay, I'm not sure if this is gonna sound like even harder or even difficult to understand, but if you the first one, if you pick the spot 2, and then you cannot pick this spot again, because we wanted to pick like the position of the ones. We're not picking ones here. We're not picking like the 0 or ones here. We want to pick the position to be ones. So if you pick the second position, and now you only have the first one or the third one left to put your other 2 ones.
Okay, so then what would with repetition look like if you can't pick the same spot multiple times?
So if it's repetition and an unordered list, it would be a back problem. I think we'll have that question the next one. So we can talk that we can talk about it in the next question. So let's first finish part B. So how many binary sequences of length 6 have exactly 4 ones?
Would be C6, C's 4.
Yes. Sorry, not 16, 6. And this will give you 15. So the third one, the C part C asks why do these 2 questions have the same answer? So there's actually, you will notice that the C33, C43, and C53 equals 15. It has the same answer as C4, C64. So there's actually a formula about this where you have your CKK plus CK plus 1 K and all the way up to N choose K. And that's equal to CK plus 1. Okay, so this is the formula. And you can see, check the exercise 42 on page 408 for this one. I'm just gonna move on to the next question because I'm not sure if we have enough time for the rest of questions.
I do have a quick question. So if it's CKK, would that equal in the problem that we had C3 of 3?
Mhm.
Then it equals CK plus 1 N plus 1, but we have it as 6, 4, which is not 3 plus 1.
I think right here it should be yeah, you're right. Okay, so you know what? I'm just gonna go back here later, so to make sure this is a correct formula. But
Yeah, I'm gonna look at it. You can keep going.
okay, so the next one here we have the problems about unordered list, but with repetitions. So this one would be a back problem. So if we have, and it says how many ways can 2 winners be chosen from a class consisting of just 4 people? So we have A, B, C, D, and we want to choose from A, B, C, D. So we have basically means that our N is A, B, C, D equals 4. And we want to choose 2. So our R is 2. And assuming that the prices are identical door prices, so we can have repeats here. And we want to rewrite this problem in the form that how many unordered list of links, which I already tell you here is length 4, can be made from set. Well, sorry, it should be links 2 here. Can be made from set A, B, C, D with repetition allows. So what is going to be the formula look like for this one? And this is the back problem. The order doesn't matter, and we can have repeats.
Would it be C of R plus N minus 1, choose 2?
Mm-hmm. And this will give us C 5, 2. And this should be equal to 10. Is that answer your question about the difference between the back problem and the set?
Yeah, I think so.
Okay. Anyone have any other question about this one? Okay.
So for the one before, it's n plus 1 choose k plus 1 instead of there's a type.
Oh, okay, I see.
Yeah.
So this should be equal to,
So c of n plus 1 and k plus 1. And then in this case, n is 5 and k is 3 because the length of the binary sequence is 5 and we're choosing 3 ones.
yes. Okay, so the next one is counting cars. Suppose we have 5 cars that dealt off of a standard 52 card deck and line up in a row, so the order does matter here. And part A asks, how many such lineups are there in which all 5 cars are all red? So we have 4 suits here, and 2 of the suits are red. And 1 suit, we have 13 cars. So that basically we have 26 red cars in total. So which technique are we going to use here? Which formula are we going to use here? The order matters, and we cannot have repeats.
That would make this a permutation problem, right?
Yes. So that will just give you P 26 choose 5, because you have total 26 red cars and you want to choose 5 of them. And that will give you this large number. And part B asks, how many such lineups are there that have at least 1 red card? you will notice the word at least. So whenever it comes up like at least, you can use the rule of complement, which you use like the total number of outcomes to minus the complement. So you can use the number of total outcomes minus the number that we cannot have a single red card. And that will give you all the outcomes that have at least one red card. And what are you gonna put for this four spot?
For the first one, would it be 52, choose 5?
Yep, because we have 52 total cars. And we just want to find out how many possible ways to choose 5 cars. And when a minus the one that we cannot have a single red card.
And that would be 26, 5?
Yep. Because all the numbers that are not red cards are also 26. And you want to choose 5. And this will give us the number of lineups that have at least one red card. And this should be okay. In part C, it asks how many such lineups are there for which all cars are the same suit. So we have 4 possible suits can choose from. And we want to pick 5 cars, which want to make sure all cars are from the same suit. So what if we want to choose 5 cars that are all space? What is going to be the outcome for that?
Would we do the rule of complements again?
Because right now we don't need to consider about the red or the color. We don't need to consider the color of the cars. And it only asks you to find out how many lineups are there in all the space. So for all the space we have,
Maybe like 13, choose 5 for just spades. And then for each suit, it would be that as well.
yeah, exactly. So we just times 4. So 13 is gonna be how many number of cars in one suit. And 5 is like how many cars do you want to choose from them. And you times 4. That give you the total number of lineups that all cars are the same suit. Okay. And this will give you number. Any questions about the first 3? Okay, so for the last one, ask about how many such lineups are there for which all cars are either the same suit or red or both.
There's a question in the chat asking, can you do 52 times 12 times 11 times 10 times 9?
52 times 12 times 11 times 9.
Times 10 times 9.
Times 10 times 9. Okay, so you want to explain this?
Can that person,
So I was just thinking like you could choose any card from the whole deck, and then after you take one out, then there's 12 left of that suit. And then after you pick one from that, another one from that suit, then it's 11, and then just keeps going down.
Okay, I see. Did you get the same answer?
I think so.
Okay. Yeah, it should be correct one. Yeah.
Okay.
So one question though, if, for example, if during the quiz or the exam, maybe like we come up with that that way of counting where we get like full credit.
Yeah. So you will get full credit as long as you have all the intermediate steps.
So if we just write numbers like that, like 52 times 12, something like that, we should have like explanation on that, right?
Yeah, you would just explain like how you would interpret all this. So like you would say the first one you want to choose 52,
Right.
and we have 12 options to choose from the same suit.
Okay, thank you.
I'll explain that. Okay, so for part D is ask how many such lineups are there for which all cards are either the same suit or red or both. So right here we have either the same suit or red or both. So what we can do is find out like the possible ways of the same suit plus the possible lineups of all red and then minus both because we overcount because we have overlaps here. So how many are there's gonna be, how many lineups are there such that they're in the same suit? You should be saying for, yeah, go ahead.
Just the answer we got for C.
Yes. So 4 times 13 choose 5. And we want to plus that they are red. That would just be the possibilities. That would just be the outcomes we found out in part A, which is 26 choose 5. And we want minus overlap. So the overlap means that they're in the same suit and they're red. So remember, we have 2 suits that are all red cards. And each suit have 13 cards. So that will give us 13 choose 5 and times 2. So that's 13 are the cards, are the number of red cards in one suit.
Could you simplify it to just be 2 times P of 13, 5 plus P of 26, 5?
Yeah. You would just simplify to that. Okay. So, and I think we don't have time. So let's just let me just do this real quick. Is ask that there are 6 to the power of 4 that equals to 1,296 different outcomes from rolling 4 distinguishable 6-sided dice. So how many of this is sum of the dice 12? So we can actually name the dice as, so we have 4 dice here, and then when the sum of them equals to 12. So we can name them X1, X2, X3, and X4. And we want to make sure that your X1 is in between this number. So based on that, we have So we know like all the 4 x's has to be greater or equal to 1. So we can now have the x1 prime, which is your x1 is equal to x1 prime plus 1. And this is 12 minus 4. That will give you all the outcomes. So the number of possible solutions to this equation is the same as to the above one. Because we know that your x prime, because we know that x has to be greater or equal to 1. So each of the x has to be greater or equal to 1. So we can minus 4 on both sides and give us this. Okay, and then we know that x1 has to be less than or equal to 6. So we just wanna, here you will give you all the possible solutions that your x has to be greater or equal to 1. But we also want to subtract that the solutions that x is greater than, that this x is greater than or equal to 7. So let's first find out the possible solutions of this one. And this is actually a bag problem, which the order doesn't matter, and you can have repeats. So you will have C, and that's your n would be 8 plus 4. Sorry, your n would be 4. You have 4 types, 4 possibilities, and you want to choose. Yes, this 8 would be your R, and this 4 would be your N. Minus 1, and that's give us 8. Choose 8, and that's all the possible outcomes when your x is greater or equal to 1. But I also want to subtract that your x is greater or equal to 7. So what are the, so if your x is greater than or equal to 7, which means your x1 can be 7, or your x2 can be 7, but you cannot have both of, you cannot have like more than one x to be 7 because you only have 12 here. So what we do here is you see 8 minus, which we're gonna times 4. 4, that means we have 4 possibilities to have one of the x to be 7 or above 7. That would be 4 times. And right now, since we're using this equation, we know that the x prime is less than x, is x prime is 1 minus, is x1 minus 1. So in fact, as long as your x prime is greater or equal to 6, so we're gonna counter that. And that will give us 5, choose 2. So the 5 actually come from 4 plus 2 minus 1, choose 2. And that's your 4 possible outcomes. This is your N and this is your R. Okay, any last minute questions?
Okay, so I'm gonna stop live stream, and that would be